Um, so we'll look at now how to evaluate the integral that comes up in the context of blackbody radiation, right? So let us call this integral mu, right? So this is the integral that we want to evaluate. First we'll just multiply top and bottom of the integrand by e to the power of minus x. Now actually if you notice, uh, if you recall this formula, which is that 1 divided by 1 minus r can be written as sum of r to the power of k, right? This is basically sum of geometric series, right? So this uh, looks exactly like that, right? So we can use that. Now you might even ask, why did we not do that here, right? Because this also looks exactly like that. Maybe just you have to just multiply by minus 1. But why we can't use that formula here is the fact that is because uh, this has a hidden condition, which is that magnitude of r must be lesser than 1. So if you have e to the power of x, this does not satisfy that condition for the range where your integral goes from 0 to infinity, right? In that range this is not satisfied. But on the other hand, e to the power of minus x in the range of 0 to infinity, it is always lesser than 1, right? So that's why we can use this formula here. So now let us do that, and we obtain the following. And taking it inside, we get now we can do just one more uh, trick, which is that instead of starting k from 0, we'll start k from 1, and then basically this will just become uh, k. So we'll just rearrange the indices like that, and we have the following expression. You can write it as k equals to 1 to infinity. So these two are exactly equivalent. You can check it for yourself. So now we'll take the summation outside, and we have the following expression. Now let us make the substitution that we take t as kx, right? So in that case, after making the substitution, this is what we will be left with, right? So you will just have k to the power of 4 and the integral from 0 to infinity t cube e to the power of minus t dt, right? Now you might recall what this integral looks like. It's a very standard integral, right? This is the gamma function, right? So this is actually basically gamma. This is just going to be gamma at, I think, 4, but whatever, this is just going to evaluate to 3 factorial. You can just look up the standard form of the gamma function. So you get basically your integral is 6 times this summation, right? This sum of series. So now we have reduced our integration to just solving this sum of series. Now this is where maybe the crux of the problem really lies, right? So how do we go about you know approaching this sum of series? So what you have to do is you have to realize that, can we find an alternative auxiliary problem where this sum sort of naturally arises, right? And it's not very obvious that you would have to look at the Fourier series of x squared. But here is an intuition. Basically, when you take Fourier series of any function, for example, you get some an and bn terms, right? So basically they're all dependent on n, so you get some kind of a series when you evaluate you know f at particular values of x and y and what sorry, particular values of x, you get various different series in n. So basically the Fourier series is able to generate multiple such series by doing that, right? So it might be uh, worthwhile looking into Fourier series of various expressions. So when you look at Fourier series of x squared, you will see that it's proportional to 1 by n squared, right? So you might have a hunch that okay, maybe if we have this, we can do something with that. So I won't evaluate the Fourier series of x squared, but I'll tell you what its form is. So it's a standard problem that you can do, and you can verify that the Fourier series of x squared looks like has the following form, right? So you can verify this. This is actually in the range from minus pi to pi. You can verify this, you can do the integral. Basically Fourier series has f of x can be written as, I think, right, you have this. And if you want to figure out what an is, you just take the integral of if you just evaluate this and integral, and you will get the coefficient of an, and similarly for bn, right? In this case, because you have an even function which is x squared, your bn terms will be 0, so there will be no contribution from sine, because sine is an odd function, right? So now what we do after having gotten this, right? After having gotten this, it still doesn't exactly solve a problem, right? Because let's say I evaluate x at particular values, then I will get some series that depends on that has the form of n squared, right? Sum of n squared, right? So that's what I'll be able to get. But but what I really want is this kind of summation, which has 1 divided by n to the power of 4 type of a form, right? So what we do here is we use something called Parseval's theorem. Okay, so basically when you're having, say, an expansion, let's say, of the following form. Basically you can also show that the squared integral basically becomes, so the Parseval's theorem has the following form. Because in this case we do not have bn, so this is the form that you get. So basically if you use this in the if you use this Parseval's theorem in the above, and we can get the following expression. We get 1 by pi, and actually why we want to use the Parseval's theorem is because it squares the an, right? So because we had 1 divided by n squared, by squaring that we get 1 divided by n to the power of 4, which is the form that we want to evaluate this series, right? So if I use this, we get x squared whole squared dx 1/2 into pi squared by 3 whole squared. Let me do it on the other page. So you get x to the power of 4 dx is equals to 1/2 a naught squared, which is just 1/2 pi to the power of 4 by 9, right? Then we have an squared, sum of, so you just get 4 minus 1 to the power of n squared, the whole thing squared, right? On the left hand side you have this, so this is what you get. Now just cancel out whatever is possible to cancel. Pi to the power of 4 by 5, sorry, it will be n to the power of 4, right? Because we had squared here, my bad. So we have 16 multiplied by the sum of 1 divided by n to the power of 4 gives you, okay, I think I have made just one error, which is that this is not a naught, this is a naught divided by 2. So a naught is really just 2 pi squared by 3, right? And this expression is pi by pi squared by 3 because you divide by 2, right? So here really you are really just actually supposed to have 2 pi by 3 squared, the whole thing squared, right? So you will actually have 4 by 18 here, 4 by 18, yeah. So basically 2 by 9, right? Yeah, now it is in the correct direction. Okay, now take 2 pi squared by 5. Now basically we have 9 45, so you have 16 times n equals to 1 to infinity 1 divided by n to the power of 4 is equals to 2 pi to the power of 4 times 4 divided by 45, right? 4 to the 8, and 8 divided by 16 is just 2. So basically your summation from 1 to infinity of 1 divided by n to the power of 4 is equals to pi to the power of 4 by 90. Now our original integral, which was from 0 to infinity of x cubed e to the power of x minus 1 dx, we had shown that it is equals to 6 times the summation of 1 from 1 to infinity n to the power of 4, right? Now since we know this value, we will just put this here, so we just get that it should be 6 multiplied by pi to the power of 4 by 90. So basically this integral evaluates to pi to the power of 4 by 15, which is our answer. Okay.